Welcome to AI Paper Podcasts. You've probably seen the just incredible leaps AI has been making lately, right? Generating text, images. It feels almost like magic sometimes.
It really does. The progress has been staggering.
But what about something really fundamental, really complex, like human motion? It's always felt like a bit of a laggard in computer vision, graphics, even robotics.
Yeah, it's definitely been a tougher nut to crack compared to static images or text.
So for the next minute or so, if you're just tuning in for the quick takeaway on what we're covering today, here it is. We're diving into a paper tackling exactly that challenge. While we've seen some progress in text-to-motion, getting to true zero-shot generalization, where the AI creates natural, diverse motions from descriptions it's never seen before, that's been the big hurdle.
A major one.
And why? Well, mostly it boils down to not having enough good training data and limits in the models themselves. But this new paper, Go to Zero, towards zero-shot motion generation with million-scale data by Kiafan and colleagues, looks set to change the game.
It's a really ambitious piece of work.
They're pushing text-to-motion towards real zero-shot capabilities with three key things. First, MotionMillion. Get this, the biggest human motion data set out there now. Over 2,000 hours, 2 million sequences. Just massive.
The scale is unprecedented.
Second, a super scalable 7 billion parameter model built specifically to actually use all that data effectively. And third, MotionMillion-Eval, a brand new benchmark designed from the ground up to test these zero-shot abilities using human reviewers too.
Which is critical for something like motion quality.
Exactly. So this isn't just some academic exercise. It's about making AI movement feel genuinely natural, responsive. Think realistic virtual characters, advanced robots. It's pretty exciting stuff.
It's huge potential implications, yeah.
All right, so that's the nutshell. Now let's really get into the weeds for the full deep dive. Before we jump into their solution, maybe you can help clarify. What exactly was holding back text-to-motion compared to, say, text or image generation? Why the lag?
Yeah, it's a great question to start with. There are a few core issues, really persistent ones. First and foremost, like you touched on, data scarcity. Seriously limited data.
How limited are we talking?
Well, think about the methods that were state-of-the-art before this, like MDM, MotionGPT, MoMask. They were trained on data sets like HumanML3D or MotionX.
Okay.
HumanML3D had maybe, 11,000 motion sequences. MotionX was a bit bigger, but still tiny by today's standards. It's like trying to teach an LLM English with just, a pamphlet instead of the web.
Right. Not enough examples, not enough variety to learn properly.
Exactly. You just don't get the diversity needed for true generalization. Then the second big problem was modality mismatches.
Modality mismatches.
Yeah, so people tried to kind of work around the data scarcity by aligning motion data with features from static images using models like CLIP.
Okay, I see the idea. Link the motion to what an image looks like.
Right. But the problem is a static image just doesn't capture time, does it? It doesn't capture the flow, the dynamics of movement. So you ended up with motions that looked, incoherent, jerky, unnatural. It just didn't work well, especially for complex instruction.
Like trying to learn a dance from a flip book, maybe.
That's a good analogy, yeah. You lose all the fluidity. And finally, even when researchers did try to scale things up a bit like the SCAMO dataset, which had about 250 hours, or the OMG model with 1 billion parameters, they weren't quite getting there.
You weren't seeing those big leaps.
Exactly. They hadn't really unlocked the full power of the scaling hypothesis. This core idea in AI right now that if you get massive data and massive models, these amazing new abilities like zero-shot generalization just kind of emerge.
Magic happens at scale.
Right. And for complex, long, compositional human motions, that just hadn't happened yet. Motion generation hadn't had its GPT-3 moment, so to speak.
So the Go to Zero authors are basically saying, okay, let's really test this scaling hypothesis for motion. Let's go all in. It sounds like a massive bet.
It absolutely is a huge bet, but it's one that paid off spectacularly in language and vision. The big unknown was, would human motion, with all its temporal complexity and physical constraints, respond the same way?
Right. Would scaling actually work here too?
And this paper is basically their answer. A resounding yes.
Okay, so if you're making that bet, the absolute first thing you need is the fuel, the data. Which brings us to MotionMillion. You said it's Colossal. How did they actually build this thing? It sounds like a monumental task.
Oh, it was definitely a revolution on the data front. MotionMillion isn't just big 2,000 hours, 2 million sequences, like you said, over 20 times bigger than previous data sets. It's also about the quality and how they got it.
Right, size isn't everything if the data's messy.
Precisely. They developed this really novel multi-stage pipeline to gather and process motion from just vast amounts of web video. It's pretty slick, actually, laid out in their figure 2. It starts with shot segmentation.
Okay, breaking the videos down.
Yeah, think of it like carefully cutting up raw footage into clean, coherent little clips, max 200 frames each. They use tools like Piscine Detect and the Laplacian operator to find natural scene breaks and cuts. Keep it focused on one action.
Makes sense. So you have these short clips. What's next? People, I assume.
Yep. Robust human detection and tracking. And this is tricky with web video, varying numbers of people getting hidden, stuff like that. They use a clever course-define approach.
How does that work?
So the course stage uses really powerful foundation models, grounding Dino to detect people based on text prompts, and SAM2 for segmentation. They set a high initial confidence bar, like 85%, to make sure they're really finding humans.
So get the easy ones first.
Right. Then the fine stage cleans things up. It uses grounding Dano's confidence scores combined with how much the detected person overlaps with SAM2's tracking the IOU to handle partial occlusions and filter out iffy detections. It's about reliably tracking the same person through the clip.
That sounds pretty robust. But video can still be jerky, right? People suddenly shifting.
Good point. That's the next step. Bounding box confidence and transition filtering. Even with good tracking, someone might suddenly jump position weirdly if the initial scene cut wasn't perfect. They check the distance the center of the person's bounding box moves between frames. If it's too abrupt, they split the clip again there. Ensure smooth continuity within each final segment.
Wow, that's meticulous. Okay, so they've got these clean clips with tracked humans. How do they get the actual 3D motion data?
That's SMPL motion estimation. They use a state-of-the-art method called GVHMR Gravity View Human Motion Recovery. It takes the tracked 2D info and estimates realistic 3D human motion using the SMPL model.
Ah, SMPL, that's the standard parametric body model, right?
Exactly. It gives you the whole 3D skeleton and all the parameters: root velocity, angular velocity, local joint positions, velocities, rotations, basically the full kinematic state.
So you get the raw 3D movement, is that it?
Almost. One final crucial step: motion filtering. This is all about ensuring the motion isn't just accurate, but smooth and natural. They look at the estimated global orientation and joint positions. Then they calculate a jerk metric.
Jerk, like how sudden the acceleration changes.
Precisely. Low jerk means smooth, natural movement. High jerk means jittery or abrupt. They use this jerk value, along with an algorithm called isolation forest, to automatically flag and filter out any remaining jitter, weird orientation flips, or physically implausible movements, ensures the final data is super high quality.
Man, that pipeline alone is an engineering feat. Just building MotionMillion seems like half the battle. But what about the other half, the text descriptions? Text to motion needs good text, right?
Absolutely critical. You need text that actually describes the motion well, and their motion captioning and augmentation is just as clever. They use GPT-4 to generate descriptions for the video clip.
Okay, makes sense. Use a powerful LLM.
But here's the key difference. They prompted GPT-4o very specifically. Not just person walks, but describe more. Include things like apparent age, body type, the style of movement, the emotion conveyed, even the environment.
So much richer descriptions than just the action itself.
Exactly. Way more semantic richness than previous datasets. But they didn't stop there. To make sure the model could handle variations in phrasing, they did description augmentation.
Oh.
They used LMA 3.18b to rewrite each GPT-4 description 20 times, keeping the core meaning the same, but changing the wording.
Wow, 20 variations for every motion.
Yep. So the model sees tons of different ways to describe the same action, which is huge for learning to generalize to new, unseen text prompts. Zero-shot capability relies on this.
So it's not just more data. It's fundamentally richer and more diverse data, both motion and text. Did this show up when they analyzed MotionMillion?
Oh, absolutely. The analysis is really telling. If you look at their figures, particularly figure 3, the semantic diversity of MotionMillion just blows existing benchmarks out of the water. The visualization shows a much wider spread, covering way more concepts.
So the model is forced to learn a broader understanding.
Exactly. Pose diversity was similar to other datasets, which is fine, but the motion smoothness was exceptional. Remember that jerk metric? MotionMillion scored 0.076. MotionX was way higher, like 0.155, much jerkier. trickier. Human ML3D was very smooth at 0.047, and MotionMillion gets really close to that gold standard despite being sourced from wild web video.
That's seriously impressive. So the data itself is inherently smoother and more natural. Okay, they built this incredible data set. What about the model? How do you build something that can actually digest 2 million sequences and learn to generalize?
Right, the data is the foundation, but you need the engine. The Go-to-Zero model itself is based on a discrete autoregressive architecture. Think similar principles to models like GPT that generate text one token at a time, but adapted for motion. They drew a lot of inspiration from those successes in NLP and vision.
Makes sense to build on what works. How do they represent the motion for the model?
They refined that quite a bit. Older formats sometimes had issues, leading to weird visual glitches like limbs bending the wrong way, inverse kinematics errors. They developed a more robust representation, this D-Touple.
D-Touple.
Yeah, it includes the root linear and angular velocities and local joint positions, velocities, and rotations. It's designed specifically to avoid those IK errors and add some regularization, making sure, for instance, joint rotations and positions make sense together. It fixes known problems, making the output much more usable.
Okay, better motion representation. But how do you feed continuous motion into a discrete model? That seems like a challenge.
It is, and that's where their efficient motion tokenization comes in. It's pretty neat. They use a technique called FSQ, finite scalar quantization. It's a way to turn continuous data into discrete tokens without needing a predefined codebook. It essentially maps the motion data onto a grid of integers.
So it digitizes the motion.
Right, but here's the really clever bit. The wavelet transformation. This was key. They apply a wavelet transform to the motion data before it goes into the FSQ encoder, and then an inverse wavelet transform after the decoder generates the tokens.
Why the wavelets?
Because just doing FSQ on the scale can actually introduce noise, a kind of jitter or shakiness, because you inevitably lose some information during discretization. Wavelet transforms are really good at compressing signals while preserving important features and smoothing things out at different scales.
Ah, so it pre-processes the motion to make the discretization cleaner.
Exactly. It significantly reduces that jitter. Their table 3 shows a big drop in the error, the deviation in acceleration, when they use the wavelet transform versus when they don't. It leads to much smoother, more realistic, reconstructed motion.
That's a smart technical detail.
Yeah.
Okay, quality data, clever tokenization. What about the main model architecture itself?
For the scalable motion generation, they went with a transformer decoder architecture similar to LMA and scaled it way up, testing models from 1 billion all the way to 7 billion parameter.
Leveraging that massive data set.
Precisely. They use the T5XL tokenizer to process the input text prompts, and they employ a mixed attention strategy.
Mixed attention, how does that work?
So within the text prompt, the attention mechanism is bidirectional. The model can look forwards and backwards to understand the full context of the instruction. But between the motion tokens themselves, the attention is causal. It only looks backward at previously generated motion steps.
Right, so it generates motion sequentially, like building frame by frame.
Exactly. This allows it to handle complex compositional instructions that unfold over time. These attention mechanisms live inside their hybrid attention blocks, HABs, which also use things like RMS norm for stable training and standard feed-forward networks.
Okay, so a huge, high-quality data set. A powerful, carefully designed model architecture scaled up to 7 billion parameters. It sounds like they have all the pieces. But the ultimate goal is zero-shot generalization. How do you actually prove that? How do you measure if it's truly generalizing to things it's never seen?
That is the million-dollar question, isn't it? And that's why MotionMillion-Eval is so important. It's not just another set of automated metrics. It's a new benchmark designed specifically for human evaluation of text-to-motion quality.
Human evaluation.
Highly.
That seems crucial for something subjective like naturalness.
Totally. They based it on actual quality standards used in industry, like animation and VFX. The benchmark has 126 really diverse text prompts. They cover everything: daily life, work, arts, combat sports, dance, even non-human stuff like a zombie shuffling.
So really pushing the boundaries.
Yeah, prompts like, a whirlwind kick is delivered by air, or the zombie shuffles forward with slow, unsteady steps. Things that require understanding beyond simple actions.
And what are the humans looking for? How do they score it?
They score the generated motions on a 1:4 scale across 3 dimensions. First, text alignment, TA. Does the motion actually match the description? Second, motion smoothness, MS. Is it fluid and natural looking? And third, physical plausibility, PP. Does it obey basic physics, gravity, avoid self-collisions?
Those seem like really solid, practical criteria. What did the results show? Did the big model and big data pay off?
Big time. Quantitatively, looking at standard metrics like FID and R precision in Table 4, their go-to-zero models significantly beat the previous state-of-the-art SCAMO, and bigger models generally did better.
Okay, the numbers look good. What about the human scores?
That's where it gets really interesting in Table 5. Their 3 billion parameter model already outperformed SCAMO on all three human dimensions, TA, PP, and MS. But the crucial finding was with text alignment.
What about it?
Text alignment improved dramatically as they scaled the model from 1 billion up to 7 billion parameters.
Ah, so the bigger models really did understand the text prompts better.
Exactly. It's strong evidence that the huge, diverse MotionMillion dataset genuinely enables these larger models to achieve better zero-shot understanding of complex language. It validates the whole scaling hypothesis for this domain.
That's huge. What about the other two metrics, physical plausibility and motion smoothness? Did they scale up too?
Interestingly, not as much. They improved, but not nearly as dramatically as text alignment. Their analysis suggests that PP and MS are actually more tied to the inherent quality of the dataset itself.
Meaning MotionMillion was already so good that even the smaller models produced pretty smooth and plausible motion.
Precisely. The baseline quality was already high thanks to that meticulous data pipeline we talked about. They actually show MotionMillion's quality on these fronts is comparable to the very clean human ML3D dataset and better than MotionX. It highlights how vital that data quality is.